In this presentation, I'll be explaining maximum power point tracking MPPT and how maximum power can be extracted from the solar panel using MPPT. Now let us see PV panel characteristics and maximum power point. PV panel characteristics includes IV characteristics, current voltage characteristics, and power voltage characteristics, PV characteristics. And in coming to the IV characteristics, it is a plot of current versus voltage. And for example, for a standard testing condition for in radiance, that is 1000 watts per square meter is a radiance, and this is the short circuit current, and this is the open circuit voltage. Therefore, this is the IV characteristics corresponding to a irradiance of 1000 watts per square meter. Now, as irradiance reduces, we can see that when short circuit current reduces, as well as the open circuit voltage also reduces slightly. Therefore, this is the second one is the IV characteristic corresponding to a irradiance of 800 watts per square meter. Like that, 600 watts per square meter radiance. This is the IV characteristic. Like that, as the irradiance reduces, you can see that one IV characteristics goes down like this one. Therefore, short circuit current reduces much and open circuit voltage also changing little bit. Therefore, that is for the IV characteristics. Now, if you calculate the instantaneous power by multiplying the voltage and current, you can plot PV characteristics. Therefore, voltage versus power. For example, corresponding to 1000 watts per square meter, if you take the product of voltage and current, it will be the power will be changing linearly and reaching to a maximum value that is going down like this one. Therefore, this is the PV characteristic corresponding to an IV characteristics of 1000 watts per square meter. Therefore, as the irradiance again reduces, say 800 watts per meter square, again if you calculate the power, it goes below 1000 watts per square meter. Therefore, like that, 600 watts per square meter, this corresponding to 400 watts per square meter, this corresponds to 200 watts per square meter for the PV curve. And as we can see that when maximum power gets reduced as the irradiance reduces. Therefore, for a given irradiance, the panel have a unique operating point called maximum power point, that is this point like that, where the output power reaches it to a maximum value. Therefore, the maximum power point tracking is used to operate the solar panel at maximum power point irrespective of the load condition. Continuing the IV and PV characteristics of the solar panel and its maximum power point MPPT. The point at which the product of voltage and the current is maximum in a VI characteristics of a solar cell is defined as maximum power point. As an example here, this is the IV characteristics of the solar panel, short circuit current, open circuit voltage. And if you multiply this current and voltage at different instance, then you can plot what is the power versus voltage. Therefore, this is the maximum power and corresponding voltage, PV panel voltage we call it as VMPP, and the corresponding current we call it as IMPP, or the product of VMPP and IMPP gives the maximum power PMPP. Now, the resistance at maximum power can be obtained by drawing a straight line from the origin to this point at the knee point. This is called the knee point of the VI characteristics, and the product of that one gives the power, and this represents the RMPP, which is equal to VMPP, maximum power point voltage, and divided by maximum power point current. VMPP divided by IMPP is the RMPP. Therefore, this is the resistance of the solar panel corresponding to the maximum power point. Therefore, the maximum power point is unique and it is located at the knee of the PV characteristics. This is the maximum power point that is at the knee of the PV characteristics. That is located at the knee of the PV characteristics, and the MPPT are used to track the peak power by operating the PV panel at the peak voltage. Therefore, if you operate the PV panel at this peak voltage VMPP, then maximum power can be transferred from the solar panel. Therefore, VMPP is a maximum power point voltage, it is the maximum power point current, and this is the maximum power, and the resistance line passing through this point, that is the knee of the IV characteristics, that we call it as RMPP, which is nothing but VMPP divided by IMPP. Now let us see the variation of RMPP for different irradiance. Therefore, this is for corresponding 1000 watts per meter square. This is the straight line passing through any point. The resistance represented by this called RMPP corresponding to 1000 watts per meter square. As the irradiance changes, that's shifting towards downward here 800 watts per meter square. Through the knee point, the resistance line passes through that one. You can see that the resistance increases. RMPP increases as irradiance reduces. Again, for 600 watts per square meter, again this straight line, the slope of this one, that represents that resistance is equal to, again it is increasing. Therefore, the RMPP, the resistance corresponding to the maximum power point RMPP, which is VMPP divided by IMPP. Therefore, the value of RMPP, that is the value of this RMPP resistance corresponding to maximum power point, that reduces as the irradiance, that increases as irradiance reduces. As irradiance reduces, the resistance increases, and MPPT tracks to adjust the duty ratio that we have seen how you can track the maximum power point by using controlling the duty ratio of the converter. We'll see later. Now here, let us see the load resistance requirement for maximum power transfer. As you know, maximum power transfer theorem, if the resistance of the source is equal to, that is represented by, as a solar panel is the source, this is the VI characteristics, and this is the maximum power PV characteristics, and this is representing RMPP, which is the resistance corresponding to the maximum power. That is the resistance of the solar panel. This solar panel can transfer maximum power to the load if the load resistance is matching or that is equal to the RMPP. Therefore, as an example here, if the load resistance is like this one, this is the point of operating point, that can extract somewhere power some less than the maximum power. But if the resistance is same as RMPP, that is this line, then it can extract the maximum power from the solar panel. Thus, by adjusting the load resistance, we can extract maximum power from the solar panel. And here again, the maximum power equal to VMPP into IMPP, RMPP equal to VMPP divided by IMPP, and panel can deliver maximum power if and only if the actual output load, that is the load resistance, is equal to RMPP, the resistance at the maximum peak power. Resistance at peak power. Now let us see the load resistance required for the maximum power transfer. As we have seen, this is the IV characteristics of the solar panel. If the load resistance equal to, say, R1, that will be operating at this point. This is the point of intersection, is the operating point, and that that is represented by the point B1. Corresponding to that power is this much. Therefore, it can deliver a power output of this much only. Now, if you increase the resistance to another value R2, that is passing through the knee of the IV curve, then that will be producing, or that can extract a power of this point B2. That point B2 corresponds to that one, or that can extract the maximum power. If you again increase the resistance to another value R3, the operating point will be B3 in VI curve. Corresponding power will become, that is represented by the point B3. That will be less than the maximum power. Therefore, in order to extract the maximum power from the solar panel, this one, that the load resistance should be same as the RMPP, that is resistance corresponding to the maximum power. Then the maximum power will be delivered to the load. Then in that case, the operating point will become this peak point. Now let us see how the maximum power point tracking can be done or can be implemented that way. For that one, this is a solar panel. This is the load. In between solar panel and load, there should be a converter, DC to DC converter. Actually, the function of the converter is that, in that case, as you know that one, the solar panel can deliver maximum power into the load if if this resistance at this input side of the DC converter, or that is the output side of the solar panel, is same as RMPP. Therefore, by adjusting the duty ratio of the converter, you can make this input or this resistance at this point same as RMPP. Therefore, the converter can be either, it can be non-isolated like buck converter, boost converter, buck boost converter, or it can be isolated like flyback, push pull, forward, half bridge, and full bridge. normally here by controlling the duty ratio of the converter, you can make the resistance looking at the input of the converter same as RMPP. That is RMPP means this one. The resistance corresponding to the maximum power RM that is passing to the knee. This resistance is called RMPP, which is VMPP divided by IMPP. If you adjust the duty ratio in such a way that the resistance at the input side of the converter is same as RMPP, then maximum power can be transferred from the solar panel into the load. Continuing the maximum power point tracking. Here, as I already explained in the previous slide, the converter which is connected between the solar panel and load, that can be either buck converter, boost converter or buck boost converter for transferring the maximum power from the solar panel into the load. Now, if you are using a buck converter, the relation between the input resistance and the resistance at the output side. Therefore, the resistance that is looking at the input side, which is equal to R out divided by D square. If it's a boost converter, that is this one is the boost converter in which the resistance at this point is equal to whatever this output resistance R out into 1 minus D whole square, where D is the duty ratio of the switch that is used in the boost converter. If it is a buck boost converter, the input resistance is equal to output resistance into 1 minus D whole square divided by D square. Now we are considering a boost converter. This is a boost converter between the solar panel and the load. And as you know, the relation of boost converter, basic relation or the output voltage and input voltage is related by V0 divided by VD, output voltage divided by input voltage, V0 by VD equal to 1 by 1 minus D, and the corresponding current is given by I0 by ID equal to 1 minus D. Therefore, from these equations, I can take V0 equal to VD by 1 minus D and I0 equal to 1 minus D into ID. Or if you take this ratio V0 by I0, which is nothing but R0, that R0 is given by V0 divided by I0, which is equal to, taking this ratio, VD divided by ID into 1 minus D whole square from these two equations. Or VD by ID is nothing but R in, the resistance at the input side of the converter, VD divided by ID. That is equal to 1 minus D whole squared into R out, meaning that a resistance R out will be reflected at the input side by this equation R in equal to R out into 1 minus D whole square. Meaning, if you are controlling the duty ratio of the switch or MOSFET of the boost converter, you can make this R in, that is the impedance of the resistance at this input side, same as RMPP. If you are making this resistance same as RMPP, the maximum power can be delivered from the solar panel into the load. Therefore, basically in this converter, you are changing the duty ratio of this switch in such a way that R in equal to R out into 1 minus D whole square, that is made equal to RMPP. Continuing the MPPT control using boost converter, and this is a solar panel, and this is a boost converter, inductor, MOSFET, and diode, a capacitor. This makes a boost converter, and this is the load resistance. As we have seen here, the resistance looking at the input side of the converter is related to by whatever this output resistance into 1 minus D whole square, where D is the duty ratio of the switch. Duty ratio is nothing but on period divided by total time period. By controlling the on period or duty ratio of the switch, you can vary the current. You can vary the resistance looking at this point for a given R out into 1 minus D whole square. And you can make this resistance equal to the RMPP, or that is this resistance corresponding to the peak, that is RMPP, which is given by VMPP divided by IMPP, that represents the maximum power. You are controlling the duty ratio and making this resistance same as RMPP, then maximum power can be transferred from the solar panel into the load. That is the basic concept of maximum power point control using a boost converter. Therefore, here R out is the resistance at the output side, R in is the resistance reflected at the input side of the converter, or the resistance seen by the panel. That is the resistance seen by the panel, which is made equal to the RMPP. Therefore, for a boost converter, the relation is that R in equal to R out into 1 minus D whole square. Continuing the principle of maximum power point tracking, here as already we have seen, there's a panel and there's a converter, boost converter, and there's a load. And by controlling the duty ratio of the switch The duty ratio is nothing but on period divided by the total time period. By controlling the duty ratio of the switch, you can vary the resistance looking at this point, so that that resistance is made equal to the resistance RMPP. RMPP is a fixed one for a particular insulation. This is the IV characteristics and this is the PV characteristics. Of course, VMPP divided by IMPP is a fixed one. Therefore, that is a RMPP for a particular radiance. Therefore, you have to control the duty ratio of the switch in such a way that the resistance reflected at the input side is made equal to this RMPP. Then maximum power can be transferred from the solar panel into the load. Therefore, adjusting the duty ratio of the converter in such a way that Rin, that is the resistance at the input side, equal to R out into 1 minus D whole square, that is equal to RMPP, which is equal to VMPP divided by IMPP. Therefore, for an example, assume that output resistance equal to 20 ohms. This is the 20 ohms. And RMPP equal to 13 ohms. This resistance equal to 13 ohms and this resistance equal to 20 ohms. Now, if you keep the duty ratio equal to 0.193, here 0.193, then Rin can be, you can calculate Rin equal to R out, that is 20 into 1 minus 0.193 whole square, which is equal to 13 ohm. Or in that case, this impedance, or sorry, this resistance is made equal to RMPP, so that maximum power can be transferred from the solar panel into the load. This is the block diagram of a maximum power point tracking, and in this one PV array, the solar PV array, and this is a load, and this is a converter. As I already explained, can be different types of converter like buck converter, boost converter, buck boost converter. I am considering a boost converter. This is a boost converter, and here we can control the duty ratio of the switch of the boost converter. That is done by this MPPT control algorithm. We'll see what is that one. And in order to work that MPPT control algorithm, you need the instantaneous value of the voltage, panel voltage and panel current. These are the two quantities required, and there will be an algorithm to control or to decide what is the duty ratio, and in that duty ratio you will be giving the switching signal to the converter switch, and so that is operating at the maximum power point, and the maximum power is transferred from the PV array into the load. There are different types of MPPT control algorithm in which I'm going to explain what is perturbance and observance P&O algorithm to extract maximum power from the solar panel. That is P&O algorithm. The perturb and observe P&O algorithm is widely used in MPPT for photovoltaic system. And this algorithm works by perturbing, or that is slightly changing, the operating point of PV array done by a duty ratio change in the converter, then observe the effect on the output power. Basically, you see that one. This is the PV plot of a solar panel, and this is the maximum power point, and towards the maximum left side of the maximum power point, if you see that one, dp delta P by delta V, or the change in power divided by the change in voltage, it is positive because I have a positive slope. This is having a positive slope means that delta P divided by delta V is positive or more than 0 towards the left side of the maximum power point. But dp by, so delta P divided by delta V, that slope of that one is negative towards the right side of the maximum power point. Or at the maximum power point, delta P by delta V equal to 0. Therefore, we are going to identify where the change in power divided by change in voltage equals 0. That is the maximum power point. For that one, what we are doing is that we are taking an operating point somewhere, anywhere, and here you are doing a certain disturbance to this point. For example, from this point, you are changing the voltage is being changed, and you will be watching what is the change in power. Then you will be watching what will be calculating what is delta P divided by delta V. If that delta P by delta V is positive, that tells that, or that indicates that that operating point is towards left side. And if delta P by delta V is negative, it indicates that it is towards right side of the maximum power. Therefore, here, in order to do this algorithm, in order to implement this algorithm, first thing is that you have to initialize the variable sign settings, or you have to measure what is the panel voltage and what is the panel current first. That's the first thing to be done. Panel voltage, instantaneous panel voltage and panel currents are measured, and you'll be calculating what is the power at that instant, Vn into In. That is, instantaneous power is being calculated. And then what next in next moment is that you are giving a perturbation. You are giving or you are increasing you are changing the voltage by an amount delta V, so that the voltage now changes to another value, that is here perturb the voltage by a small increment delta V, measure the voltage, new voltage will become Vn plus 1 and In plus 1 is the current. Therefore, the new power will become, that is Pn plus 1 will become Vn plus 1 into In plus 1. A perturbation is done from this to this point, then it will be calculating what is the new voltage and new current, and then new power can be calculated Pn plus 1. Now we'll be watching, compare the Pn plus 1 plus Pn, that is previous power is measured or compared with the present power, or Pn plus 1 is compared with Pn. Now this, if Pn plus 1, that is after perturbation, what is the power calculated, that Pn plus 1 is more than the previous power, just about that instant previous power, that indicates that the point is moving towards the maximum power point. Therefore, if Pn plus 1 is more than Pn, perturbation has moved the operating point closer to maximum power point. That is moved to closer to the maximum power point, and continue this perturbation in the same direction, that is increase the operating point by again delta V, and again up to the update, that is Vn will become now Vn plus 1 and Pn will become equal to Pn plus 1. Therefore, here you are giving a perturbation and watching the Pn plus 1 and Pn. If Pn plus 1 is more than Pn, that indicates that operating point is moving towards the maximum power point. Continuing perturbance and observance Piano technique. If Pn plus 1 is less than Pn, means that here, that is in this region towards the right side of the maximum power. If in that case, if has moved the operating point away from the maximum power point, in that case, what we have to do in order to reach the power point, maximum power point, you have to reduce the voltage. If the point is here, you have to increase the voltage. If the point is here, you have to reduce the voltage by a delta V, and the new voltage is calculated, and based on that one, new power is being calculated, that is update the voltage and power, and again this is being repeated, so that if the point is here, you will be reducing the voltage and reaching towards maximum power. If the point is here, you will be increasing the voltage and reaching to the maximum power. And one more thing is that in order to increase the voltage, means what we are doing in a converter, in order to increase a boost converter, you will be reducing the duty ratio. In order to reduce the voltage, we will be increasing the duty ratio. In boost converter, it is like that. Therefore, find each point one by one, you will be increasing and it is reaching to the maximum power. If it is here, the voltage is reducing and finally it is reaching to the maximum power point. Therefore, this is repeated. Finally, it will be operating at the maximum power point, and the algorithm runs continuously to track the maximum power point. That will be getting the maximum power. And as we already see, delta P by delta V equal to more than 0 in this region, and here delta P by delta V is less than 0. Here delta P by delta V equals 0. We want to locate this point where change in power divided by change in voltage is equal to 0. This is the Piano algorithm. As a flowchart, it is represented. Start, as I told you, you have to get the instantaneous value of the panel voltage and panel current, and then you will be calculating what is the pressure. Pressure, not power. What is the power, which is the product of voltage and current. Instantaneous power is being calculated, and that is compared with the previous instant power. If the present power is more than previous power, or if both are equal, if the present calculated power is same as previous power calculated, that indicates the maximum power point. Therefore, if the both difference are 0, meaning that both power are equal, in that case, that is returning to the final solution, that is maximum power is tracked. Now, if there is difference in previous power as well as present power, for example, if present power is more than previous power, here it comes here, delta P is equal to positive, that is operating in this region, delta P is positive. Now we have to see what is delta V, change in voltage. You have to see for change in voltage, if it is change in voltage is positive, that is present voltage is more than previous voltage, delta V is positive, then this coming here. Therefore, delta P is positive and delta V is positive, delta P by delta V is positive, that is in this region. In that case, you have to move the point towards here, or you have to increase the voltage. Increasing the voltage is done by reducing the duty ratio of the boost converter, or reducing the duty ratio, and that moves. Now in this case, delta P is positive, but here delta V is negative. Therefore, delta P by delta V is equal to negative. In that case, you have to reduce the voltage, or you have to increase the duty ratio. D equal to D minus delta, increase the duty, D equal to D plus delta D. Again, if the power output is negative, or here power output is negative means that delta P is negative. Again, if the change in voltage is equal to yes positive, or delta P by delta V is negative, in that case again duty ratio is to be increased so as to reduce the voltage, or D equal to D plus delta D. And in this case, the voltage is previous voltage is more than present voltage, or the voltage the delta V is negative. In that case, here delta P is negative, delta V is negative, or delta P by delta V is equal to positive. In that case, you have to increase the voltage. That is done by reducing the duty ratio, or D equal to D minus delta D. Then finally, that is returning back to the here, and again that is repeated until the operating point is reaches to the maximum power point. This continues. Therefore, if the operating point is somewhere here, the voltage is increased until that reaches to here, and if the voltage operating point is somewhere here, you are here increasing the voltage, or here reducing the voltage and bringing the operating point to the maximum power point. Therefore, basically you are watching what is the slope delta P by delta V. Here it is positive, and here delta P by delta V, in this case that's equal to negative.